Good morning, good afternoon, or good evening. My name is Laramie Jensen. I'm at the University of Washington, and I'm going to be talking today about some of the new data added to the IDP 2021 from the Arctic Ocean. So I wanted to give you a little bit of history and context behind GEOTRACES in the Arctic Ocean. And a lot of the work that I'm going to show you today has really built off of cruises done in 2007 and 2008 during the International Polar Year, or IPY. And after these cruises, a 2009 workshop was held in Germany to advocate for a GEOTRACES specific program to the Arctic Ocean. And from the US side, this was heavily championed by Dave Cadco and others. Originally, the plan was to do the GP15 transect next after GP16, but because of the strong scientific advocacy as well as support from international collaborators and funding sources, it was opted to do the Arctic transect next. And by 2012, planning had started in earnest for the 2015 GEOTRACES program, and it was decided that 4 cruises would go up at the same time. What this looked like was the GNO1 US cruise here in blue, the Canadian GNO2 and GNO3 cruises here in white and yellow, and the German-led cruise here in red, GNO4. And I want to especially acknowledge and thank the chief scientists, as well as the captain and crew from these 4 cruises, as well as all the scientists, both at sea and on land, who made the analyses and data possible that I'm going to show here today. So in true GEOTRACES fashion, this adds a lot of spatial resolution to what we already had in the Arctic Ocean. But it was also designed to capture important processes that might be affecting trace elements in the Arctic. So things like exchange with the Pacific and the Atlantic Ocean, which is captured here in the Bering Strait, the inflow from the Pacific into the Arctic, as well as the outflow from the Arctic through the archipelago into Baffin Bay and Labrador Sea, and then into the greater North Atlantic, captured here, and the inflow from the North Atlantic into the Barents Shelf area, captured here. And I should say that another cruise went out in 2016, the GNO5 transect to the Fram Strait, which is another really important point of exchange between the Arctic and the Atlantic, but I won't be able to talk about that today. You'll also notice that the Arctic is really dominated by continental shelf area, and these cruises, of course, were able to capture a lot of the exchange between the shelf and the ocean basins. The Arctic is also pretty unique in that it receives about 10% of the global river discharge, despite only being about 1% of the total ocean volume. So these are just some approximate locations of major river watersheds from both North America and the Asia subcontinent that flow into the Arctic. And so the Arctic surface water ends up being a major freshwater reservoir with all of this river discharge, as well as seasonal sea ice melt. And of course, atmospheric deposition was also sampled in the form of both aerosol deposition, as well as collections of rain and snow. So I wanted to start off by showing you some sections of trace metals from my own work, combining the GNO1 and GNO4 cruises. So starting here in the North Pacific and transiting across the North Pole and ending here on the Barents Sea shelf. So these sections, again, go from the Chukchi Sea, Chukchi Shelf area here across to the North Pole, approximately here, and end on the Barents Shelf. And we're looking at iron, copper, nickel, zinc, and manganese. And just looking at some of these sections, you can already begin to see where trace metal distributions overlap or diverge. So some commonalities here being the transpolar drift current in the surface of the central Arctic. So this current brings river water from the shelves across the Arctic, and this ended up being a major source of trace metals to the central Arctic. You can see here for iron, nickel, manganese, and copper, this is especially prevalent. The shelf, again, also supplied a lot of trace metals to the Arctic, and this is also advected offshore into intermediate water masses for metals like iron, nickel, copper, zinc, and manganese. Almost all the trace metals were affected by the Chukchi Shelf, as well as the presence of hydrothermal venting, which you can see here in the Eastern Arctic captured on the GNO4 transect. So that affected metals like iron and manganese. And I should say that this was already observed in other cruises like the IPY cruises, but this adds a lot more spatial coverage of that plume and the plume trajectory. I'm going to show another section now going from the North Pacific again, across the Bering Strait into the Canada sub-basin of the Arctic, and then across the archipelago and into Baffin Bay. So now combining the GNO1, GNO3, and GNO2 transects. So again, we're looking at iron, copper, nickel, zinc, manganese, going here from the Chukchi Shelf all the way across the archipelago into Baffin Bay and out into the Labrador Sea. And you'll again notice the presence of the shelf here, and that you can trace that shelf water that's pulled into this intermediate halocline water mass across the archipelago in some cases. And this is certainly influenced and augmented and modified by local river sources, as well as the role of tidal resuspension. And you can even see some local remineralization here in the older, more isolated waters in Baffin Bay. And importantly, we're keeping an eye on this region because this is an outflow into the Labrador Sea and then into the North Atlantic. So this could potentially have an effect on our global elemental budgets for these trace metals. I want to now talk a little bit more in detail about copper and nickel and some of my own work looking at a copper and nickel synthesis across all 4 cruises in the Arctic Ocean. And I'm showing these profiles just to give you a sense for how good intercalibration was for the trace metals across all 4 cruises. So we're looking at the US and Canada cruises, as well as between the US and German cruises. And the overlap was quite consistent, very good intercalibration. And you can also notice how similar the profiles of nickel and copper are in the Arctic to each other, which is not necessarily what we expect based on what we know globally about copper and nickel. And actually, this led to an interesting result, whereas across the entire Arctic, copper and nickel were linearly related to each other. So we're looking at copper here on the y-axis and nickel on the x-axis. And I'm showing the Arctic data in color, colored by depth. And in the background in gray is all the data from the IDP 2017, so the rest of the global ocean in terms of copper and nickel. And I've highlighted profiles from the Atlantic and the Pacific to give you a sense of how copper and nickel are generally related throughout the water column. And you'll notice that in kind of reverse to what we see globally, the highest concentrations for copper and nickel are at our shallowest sample depth, and the lowest concentrations are at the deepest sample depth. And if we look just at the Arctic, we can see that this is really driven by high concentrations in the surface coming from those transpolar drift stations, and very much anchored by low deep water concentrations that were quite consistent, very homogeneous. So in this way, copper and nickel actually become a really nice example of what we've learned about trace metals in the Arctic Ocean, especially in combining now multiple cruises together. So we again see the influence of that transpolar drift that forms the maximum in the surface for concentrations of copper and nickel, shown here. And that work has already been really nicely summarized in a synthesis paper by Matt Charette and others in 2020. The role of the Western Arctic halocline, so this halocline that's being produced on the Chukchi Shelf here and pulled into an intermediate water mass, that very much dominated trace element distribution throughout the Arctic. And that's mostly because of the role of the Chukchi Shelf here. Whereas in contrast, the Barents Shelf was not a significant source of trace metals like copper and nickel. And you can see that there's no halocline that's nutrient or trace metal rich in the Eastern Arctic. Another really interesting feature that was observed in papers looking just at one cruise or combining the cruises was a gradient in deep water concentrations between these subbasins in the Arctic. Notice that metals like nickel and copper are slightly higher in the Eastern Arctic compared to the Western Arctic. And now in combining these cruises and multiple different data sets, we might be able to investigate why that is. So I'll just leave you with some of the major points about trace metals in the Arctic that we've now learned in looking at all of this data together. Physical circulation is a major control. We have a clear absence of normal vertical biological cycling that might produce remineralization signals in the deep water. The rivers and shelves are major sources of trace metals like copper and nickel to the Arctic. And deep water could provide some insight to elemental cycling, especially in the absence of our typical biological signals. With that, thank you, and I welcome any questions.